Hey, hello everyone. Welcome to today's contest discussion of Goodbye 2025 contest on 27th December. Let's start the discussion. We will be discussing A, B, C, and D problems. So let's begin with the very first problem. The problem name is Yes or Yes. The problem states last Christmas, your friend Faredo gifted you a string S consisting only of characters Y and N, represented by yes and no. That is why yes is represented by y and no is represented by n. You can repeatedly apply the following operation on s. What is the operation? You can choose two adjacent characters and replace them with their logical or. Formally, in one operation, you can choose two consecutive characters si and si plus 1. Then insert a single character y if both of them are y, else insert a n. If one of them is y, insert a y, or if both of them are n, insert a n. Note that after each operation the length of string decreases by 1. How? Because we picked up two characters and inserted just one. Unfortunately, Faredo does not want you to combine yes or yes. What does this mean? A yes cannot be combined with another yes. That is, y comma y can never be picked up for an operation. Now we need to determine whether if it is possible to reduce S to a single character by repeatedly applying the operation above. Okay, so what does the problem say actually? The problem says us to apply the given operation, pick up two consecutive string, pick two consecutive indices and replace it with or of those two indices. Okay, and what is our aim? Reduce the string to a single character. All right. And what is the restriction? We can never pick up y comma y. Okay, two consecutive y's can never be picked up. Okay, so let's start with the analysis of test cases. What are the test cases given to us? The first test case is y comma y. Okay, so we are restricted to pick up y comma y, and that is the only substring present. Okay, so we can never pick up this particular substring. So that is no operation can be applied. That is why answer is no. Now coming to this particular substring or string, n, we can pick up the only available substring, that is index 1 and index 2, and replace them with the or, that is n. And this particular new substring is a single this particular new string is a single length string. So the answer is yes, because we have reduced it to a single character. Now to this particular string, we can apply operation in any way. That is, pick up these two and it reduces to ny, or pick up these two, it reduces to ny again. Why? Because the or of n and y is y. Now pick up the only available substring, that is ny, and reduce it with y. Alright, so answer is yes. Now coming to this particular test case, it is very good to analyze this particular test case clearly, because this leads us to the answer. So we have only one option. Okay, that is this. Okay, we have two options. This n can combine with the right y or the left y. Whatever be the case, the final output gives us y. All right, and can an operation be applied now? All the string consists of only y's, and picking up two y's is not allowed. So no operation can be applied right now. So answer is no. Now this particular string, start applying operation from the left, reduce these to a single n, then these two n to a single n, and so on. And at last we are left over with a single n. All right. So yes, this is possible. Now coming to this test case, it is the similar scenario. Okay, similar as what we discussed above. It consists of only y's, so no operation can be applied. So answer is no. Now for this particular test case, uh, whatever operation you apply, just a single one n will be reduced. All right. So uh, after each operation, then the count of n will be reducing, and after appropriate number of operations, a single y will remain. So answer is yes. What is our observations with the help of all these analysis? We can observe that if we pick up n comma n, we are left over with a single n. That is one n is removed. All right. And if we picked up n y, we are left over with a single y. Again, one n is removed, or we can pick up yn, and again y is left over and single n is removed. But we can never pick up yy. Okay. So whatever we pick up, one single n is removed. So there is no damage done to y. That is, the number of y's remain constant. All right. Because no particular operation reduces the number of y's. And can all n's be removed? Okay, if the neighbor of this particular n is a n, then also it can be removed. If it is a y, then also it can be removed. So all n's can be removed. Okay, so what does this observation lead us to? What conclusion? Can we conclude that since all n's can be removed, so n should not be a part of our consideration to reduce the number of characters. And since no y can be removed, the count of y should be less than equal to 1. Alright. Why? Because we want at the last that only one character remains in our string. And if the count of y is greater than 1, the number of y's cannot be reduced. So at the end, the number of y's will always be greater than 1. Alright. So what is our final answer? If count of y is smaller than equal to 1, output is yes, else output is no. Alright. So let's move to the implementation part now. So this is the implementation. We have taken the string as input, and we have counted the number of n's and number of y's. The number of y's is represented by ct1, counter 1. So if the string is n, then increase the counter of zeroth counter. And if the string is not n, that is it is y, that is if the character is not n, it is y, then increase the counter 1. Now if the counter 1 is smaller than equal to n, then we print yes, the answer is possible, else we print no. All right. You will be given the link to the solution after the contest in the description. You can refer to that. So let's move to the next problem now. So let's move to the second problem now. The problem name is imposter or sus. We are given a string W consisting of lowercase Latin letters. Uh, it is called suspicious if and only if the following condition hold. This letter S appears at least twice and at least one. Okay, for every occurrence of U, the two nearest occurrence of S are the same number of characters away from U. What does this mean? Okay, so it says that for every U, what does this say? For every occurrence of U, that is, for every U, the nearest occurrence of S are the same number of characters away from U. That is, the next S to the left of it and to the right of it. The distance between this u and the nearest to s is same. Okay, let's say the two nearest s are on the same side. Can this be possible? Because this particular introduction of s itself changes a distance. That is, it is one distance away and this is two distance away in this condition. So the two s cannot be on the same side for the first scenario. Now the second thing, uh, this particular s is at same distance from you as this particular s. This is what the condition given to us me. Okay. After watching you finish a string task, your friend aka has gifted you a string R consisting only of letters S and U. You can perform the following operation on R. Choose an index I and set Ri to S. Determine the minimum number of operations needed to make R suspicious. Okay, what is our task? We are given some strings and we can replace a U with S by applying one operation. Now we want to make our string suspicious with the minimum possible of operations required, minimum number of operations possible. Okay, so let's analyze some test cases. Okay, for the very first case, can multiple U's appear consecutively? Okay, let's say these are some U's sandwiched between some S's. Now for this U, the nearest S is this to the left side, and to the right side that S is this. So the distance is not same now. Okay. So if there is a S to the left of it, that is nearest to it, there should be a S to the right of it. Alright. Now to the left of U, what are the possible scenarios? There can be a U or there can be a S. If this is a S, then every U is sandwiched between the S's. If there is a U, then this leads us to the same scenario as above, as we have communicated before. That is, for this particular U, a S should be present to the right of it. So again, this particular U is now sandwiched between two S. So a observation which we can note down is every U is sandwiched, okay, between two S in a suspicious string. Alright, this is our observation. So what is the final look of a suspicious string? There are some S and there is a U sandwiched between some S, then again some S, a U, then US, 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 and then SSSS, something like that. Okay, what does this mean? Before and after every U, there should be a S present. Alright, if there are some consecutive S, we have nothing to do with them. Now let's start with all the test cases given to us. For the very first test case, it is SUS. Now every U is sandwiched between a S, so no operation is required. Alright. Now in this test case, there are some consecutive U's which is not possible as we have discussed. So we must replace some U's with S. Okay, let's say we replaced this U. Okay, one more thing, that is we must have at least two S's. Alright. So it's better to replace this U with S. Why? Because if we had not replaced this particular U, we had replaced this U, then to the left of this U there is no S. Alright. So the condition is still not satisfied. So it's better to replace this particular U with a S. Now, okay, this particular U with S. Now, for making this particular U sandwiched, this U should also convert to S. And this U should also convert to S because the end element can never be U because it is not sandwiched. Alright. So what are the minimum number of operations required when all the characters were U? For the case of odd and for the case of even, let's analyze it. For the case of even, what did we see? We need n by 2 plus 1. Alright. Because replace the first and last characters, then for the middle elements we have odd number of okay, we have even number of elements left, and every one of them will be replaced. So for the last two characters 1, and for the remaining n by 2. All right. Okay. Okay, so what did we observe? For even it is n by 2 plus 1. Now for odd, let's say there were 5 U's. So we start replacing with the last and the first. Now the remaining consecutive U's is again a odd value. All right. And we need to replace every third, okay, every first, third, fifth, and so on. So this is again n by 2 plus 1. How? Because there were 5 characters, uh, and we replaced 3 of them. 5 by 2, floor of 5 by 2 is 2, and plus 1, it is 3. Alright. So we'll note down the pattern because we will use this later in our code. Now this particular scenario is consisting of all S's, so no need to replace. Okay, so what is the answer for this? Answer should be 3, which is given. Now let's move to next test case. We have 2 U's. Alright, so for 2 U's, such that the end is itself sandwiched by a particular S. So no need to replace this particular U. Okay, let's analyze all the possible cases. Alright. Okay, so let's move to analyze all the possible cases. We analyzed one case where all the U's were present. Okay, if the whole string consisted of U, then this is our, we can say, formula. Alright, let's write it down. All U, what is the formula we calculated? It is n by 2 plus 1. Okay, so if there is a U and one of the corner of it is surrounded by S, what should be the formula? Let's analyze for both odd and even. Okay, so for odd case, again n plus 1 by 2 because, okay, is it n plus 1 by 2? Yes. Why? Because we need to replace the last one for sure, and this one again. For even, it is, we will need to replace the first one, then this one. Okay, all right, that is it. So for even case, we need to replace it by n by 2, and for odd case, it is replaced by n by 2 plus 1. All right. So overall, we can write it down as n plus 1 by 2, floor of n plus 1 divided by. All right. How? Because for odd, it is n by 2 plus 1, and for even, it is n by 2. So overall, n plus 1 by 2 gives us very same value. Why? Because if n is even 4, then 4 plus 1 is 5. 5, one extra value is added from 4, which when divided by 2 will give 0.5 as the answer. And taking the floor, it gives us 2 again. So n plus 1 by 2, the floor of n plus 1 with 2 gives us the very correct formula. Now let's move to the third case where the U's are sandwiched between S's. For this, let's analyze the odd case and the even case. For odd case, just replace one of them. All right. For even case, we need to replace this and this. So what is the formula finally. For 3 U's, we need 1 S, n by 2. Alright. And for 4 U's, we need 2 S. Again, n by 2. So the final formula comes out to be n by 2. Alright. So this gives us the conclusion that if the string contains of all U's, then replace it with, okay, replace it with some S, and how many S are required? N by 2 plus 1. Floor of n by 2 plus 1. Now, if the U's are a substring and they are present in some corners, alright, because this U is not surrounded by some S, and this U is surrounded by some S. For this scenario, the formula came out to be n plus 1 by 2. And for the third case, a U's are surrounded by S on both sides. For this, the formula came out to be n by 2. Just observation, write it down and try to find out how many number of uh, S needs to be replaced. Keeping in mind that the first and last need to be replaced every time if there is no S at the border, and if there is a S at the border, no need to replace the last element. Start from the second. All right. So let's try to apply this particular formula on all the test cases given to us. So we were on the third test case. It was UUS, UUU. Okay. So there are two U's present in the corner. Okay. So for corner, what did we say? N plus 1 by 2. So 2 plus 1, 3 by 2. It is equal to 1. All right. So we can replace this particular U with a S and it is done. All right. But this is what one operation mean. Now for this, there are 3 U's and they are in a corner. So what is the formula? Formula is n plus 1 by 2 again. What is n? 3. 3 plus 1 by 2, which is 4 by 2. That is 2 again. Why? How? The corner needs to be removed every time. Now, this particular U is surrounded, not sandwiched by S. So replace it with a S. So how many replacement were done? 2. So n plus 1, that is 3 plus 1 by 2, number of operations. That is it. How many operations did we apply? 1 plus 2. So total number of operations applied is 3. Similarly, for this case, this is not sandwiched. This is a case of n plus 1 by 2. That is one border. How many elements are there? 6 elements. 6 plus 1 by 2, 7 by 2. It is 3 again. That is the answer. Similarly, 1, 1, 2, and 6 for these cases, which you can do it easily. For this, it is a border scenario, n plus 1 by 2. So one answer. For this, it is a sandwiched case. So n by 2, 3 by 2, it is 1. And for this test case, this is sandwiched, n by 2, 1. This is not sandwiched. Okay, this is again sandwiched, 1 by 2, it is 0 operation. For this, it is sandwiched again, 3 plus 1 by 2, it is 2 operation. Now for this, it is the very first scenario where all elements are used. So replace it with n by 2 plus 1. Alright. What do n by 2 plus 1 mean? Seal of n by 2. Alright. Just divide it into odd and even scenario and find out the answer. So let's move to the implementation part. So this is the implementation. We have a string. Find out the size of string using the function. Now the answer contains the number of operation we need to apply. We are finding the consecutive use using this operation. If the current element is S, no need to include it or apply our operation here. Just move forward. Now if we find a U, find all the consecutive U's starting from current index. So apply a while loop while we find a U j plus plus until j is smaller than n. Now we find a S and we stopped. So j minus minus, this gives us the index of very last U. That is, if we started from here, move forward up till third index. We moved to fourth index to stop. So minus minus, and we came back again to third index. Now, if I is equal to 0 and j equal to n minus 1. That is, it is the case where whole string consists of only use. What was the formula? N by 2 plus 1, or ceil of n by 2. So what is n? It is the length. How is length found? It is found using j minus I plus 1. Okay, total number of elements in current substring. Now the second scenario, it is a border scenario. That is, it is the substring is either starting from starting index or ending at the ending index, not both. So for this case, the answer was floor of n plus 1 by 2. Alright. So n, that is the length of substring, plus 1 by 2. For the third scenario, the answer was floor of n by 2. So length divided by 2. At last, up to which position we have already considered, move I to that place and let the loop continue. So this is it. At the end, print the answer. So let's move forward to the third question now. So let's move to the third problem now, which states that there are n children standing in a line where the niceness of ith child is ai. Santa is deciding which children belong to the nice list and which belong to the naughty list. An integer x is initially set to 0. Santa will perform the following operation n minus 1 times. Choose the first or second child in the list and remove them from the line. Let w be the niceness of the chosen child. If the first child is chosen, add them to the nice list and add w to x. If the second child is chosen, add them to the naughty list and subtract w from x. Note that after all operations, exactly one child remains unassigned to the list. Determine the maximum value of x that Santa can obtain after n minus 1 operation. So what does the problem say? It say that uh, initially Santa had some children standing in a line with some values. All right, niceness values. Okay, for let's copy the test case. For example, in this test case, the very first test case, there were two childrens, 2 and minus 3. So Santa has two choices. He can choose the very first child and add it to his list. That is, 2 is added to his list. So initially the list was having score 0. It will have score 2 now. Or he can subtract the second element. That is, we can subtract minus 3 and the value is equal to 0 minus minus 3, which is equal to 3. Alright. Now for the second test case, he has 1, 4, 3, 4. So he can pick up the first element and add it to the list. Then he can pick up the second element, then add it to the list, then third element, add it to the list. Why? Because all the previous elements have become have been already utilized, so they have been reduced from the list. All right. So every element becomes the first element, and except the last one, every element is chosen. Now coming to this particular scenario or this test case, minus 4. Okay, what will Santa want? He will want that the negative values should be subtracted. So overall they become positive value. Why? Because minus of something, okay, minus of minus 2 is equal to plus 2. So subtracting a negative value is good for us because it gives us a positive value added to our number. And what for the positive values, he will want that they will be added to our number instead of being subtracted. So what is our aim of Santa? Positive, add, negative, subtract. Okay, this is the aim of Santa. Okay, let's have some more observations now. Okay, Let's say there were some numbers A1, A2, A3, A4, A5. Alright, Santa wants, okay, after doing all these operations, one number will be remained for sure. Let's say Santa finds out that particular number. He says that I will not pick up A3 for sure. Then what will happen with all the other numbers? Okay, so for the previous numbers, okay, what is the very first observation? A1 will always be added. Why? Because to be subtracted, it has to be at the second index, and a particular element can move only to leftward, not to the rightward. Okay, so A1 will always be added. Now, what about A2? If Santa wants A2 to be added, he will first remove A1. Now A2 becomes the first element. So add A2. If Santa wants A2 to be subtracted, Santa can remove A2 right away and then subtract it from the current number, and the string becomes that is array becomes like this. Now what about A4 and A5? We know that A3 will never be chosen. So do A4 and A5 have the independence to move to the first index? No, they will never have, because if A4 wants to be chosen, then A3 needs to be chosen for sure for A4 to become the very first element. Alright, what did we say? For A4 to become first element, A3 must be chosen. Alright, and if A3 is not chosen, A4, A5 and every numbers after A3, they will be subtracted. So if A3 is not chosen, the suffix of A3, that is A4 and A5, will be subtracted. Now what about the prefix of A3, the number that is not being chosen? There were some numbers. We had already concluded that A1 will always be added. Now if A2 is negative, Santa will want that it should be subtracted. So remove it right away. And now a new number comes. Let's say B. B is positive. So what will Santa do? Just first remove A2 because it was to be subtracted. Then number becomes like this. Now A1 is to be added. Remove A1 and B becomes the number to be added. Can you see that the scenario is just like the previous scenario? Initial scenario, we had a string. Okay, we had an array whose first number had to be chosen. All right, and uh, as positive, and second was to be chosen as negative. Now again, the first number is as such that it should be chosen as positive, and we have some numbers left. So okay, it becomes like the previous scenario. So we conclude that with this construction, what construction? If the number is to be chosen as positive, take it to positive. If the next consecutive numbers, okay, let's say we had a set of B1, B2, B3, and so on that were negative, that is, they needed to be subtracted. So keep B as it is. First remove B2, B3, B4, B5, and let's say B4 is a number that is to be added. So first remove B1, it is subtracted. Now B2, it is subtracted. Now B3, it is subtracted. Now B4 comes. So remove B4 need to be added. So remove B, and B4 becomes the very first element, which is again the scenario where we started from. Okay, so we are starting from a scenario, doing some operation which are very much optimal for us. That is, we are choosing positive numbers for adding and negative numbers as subtracting, and we come back to that same scenario. So we come to a conclusion that acceptable, that is the very first number, all numbers to the prefix of non-chosen number is chosen optimally, added for positive and subtracted for negative. Alright. And for suffix, except the non-chosen number, all are subtracted. Alright. So if we had a number, we can uh, count the okay, we can pre-compute the answer for prefix. How? For every index, if it is positive, add it. If it is negative, subtract it. And for A1, just add it. And we can also have the suffix sum maintained. So while pre-computing, using pre-computation, we can have the uh, prefix value, contribution for each index. Alright. So iterate over each index. Let's say that index was the one that is not to be chosen. Compute the value that we get by choosing that particular index as the answer. And then uh, the max of all the answers among all the chosen values is our answer. Alright. So what do we do? Our algorithm would be iterate over all indices, say this index is not to be chosen. Alright. Then compute the answer using prefix plus suffix. How to compute prefix and suffix? We have already discussed it. And over all the iterations, the maximum value we have got, that is our answer. Okay, so let's move to the implementation part now. So we take the number of elements in our vector. We take the vector as input. Now we compute the suffix sum. How do we compute the suffix sum? It is just the normal computation, and the suffix will contribute with negative sign. Okay, it is subtracted. So suffix at I is equal to suffix at I plus 1 plus vec at I. So uh, this will go on. Now let's say the very first index is the index that is not chosen. So apart from the first index, all the uh, rest numbers, they will be subtracted. So for that case, the base case of answer is suffix of 1, and minus sign denotes that all the numbers are subtracted. Alright. And what is cur? Cur represents the prefix value. That is the very first element that needs to be added, and rest element, if it is positive, add it, else subtract it. So let's move to the second index. For second index, the prefix value is vec at 0, that is the very first index that is added. And apart from first index, the second index onwards, all the elements are subtracted. So minus suffix of I plus 1. Now in the prefix, the current index need to be added with absolute value. Why absolute value? If it is positive, we add it. If it is negative, we subtract it. So overall, we are adding the absolute value of a number to our answer. Alright. So add it to cur and move forward. For the next index, this cur becomes the prefix, and we already have the suffix. And among all these computations, the maximum answer what we can get, that is our final answer. Alright. Let's move to the fourth problem for now. So let's move to the fourth problem for now. It is Xmas or hysteria. Franklin is plotting a Christmas attack where he cast a spell mass hysteria on village of eels. There are n eels numbered from 1 to n, where ith eel has health value hi and attack value hi. Okay, ai. Initially, hi is equal to ai. That is, health is equal to the attack value for all the indices, and all ais are distinct. All right, all the health values and all the attack values are equal for every index, and they are unique for each index. All right. When Franklin cast mass hysteria, the following process is repeated. Choose a pair of distinct living elves X and Y such that elf X has not attacked before. If no such pair exists, terminate the process. Then, if such a pair exists, then elf attacks elf x attacks elf y, decreasing hx by ax. Additionally, due to recoil, hx is decreased by ay. That is, they both attack each other, and health of both of them is reduced according to the opponent's attack value. Note that ax and ay remains unchanged. In the process will repeat until it is impossible to choose a valid pair of elves. It can be shown that my mass hysteria terminates after at most n iterations. Given an integer m, construct a valid sequence of attacks such that exactly m elves are alive when the process ends, or determine no such sequence exists. Okay, what does the problem statement say? Problem statement say that we have some health values. Okay, let's copy the test case. We are given the number of else, and the number of else we want to be surviving at the end of the game, and the health and uh, attack value of each elf. All right. Now we pick up two pair of elves such that one of the element of the pair has not attacked before. All right. He has not been chosen to attack. He can be chosen to have been attacked. That is, the second element chosen attacks that element, but that element do not attacks the chosen element. Uh, Although he will give the recoil, which is equivalent to the attack value, but he do not attack right now. So he do not attack right now. Let's say we have chosen the pair 1 and 2. So what happens? One attack 2 with uh, attack value 1. So health of 2 is reduced to 1, and 2 attack 1 with attack value 2. So health is reduced to -1. So 2 is surviving and 1 is dead now. Now let's say uh, this is the operation coming forward, and let's say 2 has attacked 1. So 2 will not be attacking again. It can be attacked by some other index, but it won't be attacking any other index again. Alright. And 1 is dead now. So it won't be counted in the 2 surviving elements which are left at the end. Now, maybe we can say 4 to attack 2. But what will happen after this? 4 has already attacked, and 4's health will go to 2, and 3's health 2 will be dead with health value -3, and 3 will health 3. Now 3 has not attacked till now. We have 2 surviving elements, but 3 has not attacked till now. That is what our question asks. That after all the operations, if there are two distinct indices such that one elf or one of the index elf has not attacked before, that will have to attack, or the operation will continue forward. So 3 will attack 4 now, and 4 will be dead. So this is not a correct possible construction that we talked about. what could be a possible correct construction? Okay, after this particular scenario, what could be a possible correct construction? 2 is surviving. 2 has already attacked 1, so 2 need not be a part of pair after this. Let's say 4 had attacked 3. So what is the health of 3? -1. And what is the health of 4? 1. Now we have 2 surviving elements. Has 2 attacked before? Yes, 2 has attacked 1. Has 4 attacked before? Yes. Yes, 4 has attacked to 3. So they both can't be a part of any new pair, right? So they both have uh, some healths remaining. So there are 2 elements remaining, and this is a good construction. That is a construction which leads us to this possible scenario. Now let's move forward to some observations. The very first observation mentioned in the problem is that all, okay, we were here. Okay, let's copy paste the test case again. What are the observations we discussed? The very first observation was that all elements are, okay, okay. The very first observation is that all elements are unique. All right. So for the first time, a number is chosen. That is, let's say 1 and 2 are chosen. So one of the element will be dead for sure. All right. So for a pair of chosen, for a chosen pair, one element will be dead for sure. All right. Even if the elements are not unique, that is 1 comma 1, then also although this is not a scenario, but it will be upcoming in future. So if such a scenario comes, that is health of 1 is 1 and health of 1 is uh, another number whose attack value was 2, let's say, it is also 1, because this 2 has already fought with some other elements, so its health is currently 1. So if these both fight, all both of the numbers will be dead. All right. So we have come to a conclusion that since attack values are unique, attack values are unique, and health value is always smaller than equal to attack value. So, okay, what does this mean? That is, the health value of second element is now 1, but it can never be greater than 1. Greater than 2. All right, it can be at most 2. So if another chosen attack value was 3, it is 100% scenario that this 3 will kill the element with attack value 2, whatever health it has, whatever number of elements he has already fought uh, initially. Since the attack values are unique, it is destined that for each pair one element will be killed. All right, so this is our first conclusion. So for cases where number of surviving elements is greater than uh, okay, the number of surviving, okay, each surviving elements must have fought before. All right, so they must have had made a pair. All right, So m into 2 are the total number of elements chosen so far. So for m elements to be surviving, there should be at least 2 into m numbers present. Why? Because each element must have made up a pair with some other elements and he is surviving. All right. So a unique element must have been chosen. So if this m into n is greater than the total number of elements we have, the answer would be -1 for sure. All right. Because these number of pairs can never be made up. We can never make such number of pairs. Now let's move to another scenario. Let's say we have some m. All right. Let's say we have m is equal to 2 for any good test case. Let's say for this test case, we have the value of m as 2, m as 1. So what is the number of pairs that need to be made? One pair. All right. So two elements are required and 2 is smaller than equal to n. N is 4. So -1 is not the case here. Now, let's say we say the very first two elements to fight, and we always want that the surviving element is the attacking element. Why? Because at the end we will be left over with some elements. All right. And what will be, let's say we are remaining with m elements, what will be the restricting factor to us that will tell us that no, you cannot stop here, one more elements need to be dead right now? It is that one of the elements have not attacked so far. So we would want that all the maximum elements that are surviving, they should be having a fight beforehand. Because if they have attacked beforehand, that particular restriction do not hold us back when only m elements are remaining. All right. So let's say we tell the first two elements to fight among themselves, and the value with higher uh, attacking power is the one attacking. So the health of 2 will be -1 and the health of 3 will be equal to 1. Now there are two elements remaining, 4 and 5. And we have done one fight and one surviving element has value 1. Let's already see that we have already sorted all the elements in increasing order of their attack value. Now, if this particular 4 attacks this 3, okay, what is the health constraint for this particular element? Its health will be somewhere in range uh, 0 to, okay, not 0, 1 to 3. Okay, smaller than 3 for sure, because it has fought with 2. Okay, let's say here it can be 1 as well. So in this case, the remaining health will be equal to 2. That is what I am saying. Here, the health is equal to 1. But what is the possible values? Because this particular part is sorted. The possible value is between 1 to 3, which is smaller than 4. Okay. Now, let's say we say this 4 to fight with this 3. This 3 has health value smaller than 4 for sure. Okay, because initially all the elements are unique, and this value should always be smaller than the attack value. Health value after this prefix has already fought is smaller than the current attack value, and the attack value is smaller than the attack value of this particular number, and this number has not fought before, so its health value is always also greater than the health value of this number. So if these two both element fight, only 4 will be surviving, and with what value? 4 will be surviving. Let's say 4 has attacked, and what is the value 4 has? It is 1. All right. Now 5 has not fought before. There is one pair remaining. Now 4, 5 fought. 5 has attacked. -1. and here 1. Got it? What did we do right here? Okay, let's say we have made up m elements who have already fought, so they are not uh, dying for fighting now. Okay, because it is no, there is no restriction for us that they will fight later on. Now, if the rest elements are removed somehow, and these m elements are only remaining, there is no restriction to us that they have all not already fought before, so they must fight. So this can be a possible answer, but it is not true. There are some elements present to the left of it, but we know that attack value of all these m elements are smaller than these elements. So slowly inculcate all these numbers into these m elements. Pick up an element from m, and let's say it fight with 7. It is sure that that element will lose because its health value is smaller than 7, and it is sure that 7 will survive because its attack value is smaller than 7. So we have removed one element and we have inserted one element, and the scenario is same as it was in the starting. We have m elements, and if somehow all these elements are removed, this can become our possible answer. Then inculcate 9, then inculcate 10, then inculcate 15 into our m elements. At the end, we are left over with m elements, which is a possible answer. So print it. So what is our construction? Arrange a fight of first m elements with next m elements. Alright, now we have surviving m elements who have already fought before. Okay, what who have already attacked before. Now, for rest elements, they have attack value greater than health value and attack value of these m elements. For sure, because we have already sorted in the increasing order of attack value. Slowly inculcate these remaining elements into the m-sized list. Alright, now is our construction over? No. We have already decided that such m elements should exist. Okay, there is at least one element that will fight with this 9 to be inculcated in this list. What if there is no element? That is, the value of m is 0. We have an extra case for m is equal to 0, which is a edge case for sure. We need to have a construction for this as well. Let's have a condition where m is equal to 0. This particular condition. For this condition, m is equal to 0. So what happens? We want a construction where at the end all the elements have fought among themselves and all are dead. Okay, what do we have in observation? If uh, we let some elements fight such that first all the elements are sorted in attack order. First element fight second element, then first element will be dead for sure, and second element will be surviving for sure. Then second fight third, second dead, third remaining. Third fight fourth, third dead, fourth remaining, and fourth has attacked before. All right. This is one of the observations we have. Now, what do we want? We want the very first uh, intention of us will be that we want all the elements to be dead. So let's try what is the element with the maximum probability of surviving. It is the maximum element for sure. All right. So let's try how we can kill the maximum element. We started with 3. We came to element 2. Can we kill 3 using 2? No. So move forward. Can we kill 3 using 2 and 1? Yes, we can. So use both of them to kill 3. At the end, 3 will be also killed. And because these two are fighting a element with higher attack value, these two will be killed as well. Alright. So this is as well a good scenario. But is it the only scenario we have? There can be a scenario where we are left over with some elements after this highest value is finished. For example, we have such values. Alright. So this 6 will be over after we let it fight with 5 and 4. Alright. Why? Because 5 plus 4 is equal to 10, which is greater than 6. 5 will inculcate a damage of 5, so health value is 1 now, and 4 will inculcate a damage value of 6. 4 to health value 1, which is leading us to minus 3. Alright. So if we use these both, we can for sure defeat 6, but we still have some leftover elements here. Alright, and whatever the health of this value is, its attack power will always be 4. Alright, so let's say these all fight among themselves, and only this 4 is surviving. Afterwards, we can say 6 to 5 this 4, 5, and 6 to 5 this 4. And what is the final answer? This 6 will be remaining. Okay, so this 6 will be dead and this 4 will be dead as well because this 4 has fought with 6. So we want a construction such that this particular uh, prefix is dead before this part starts. And after this fight, 4 is surviving. Do we have such a construction? Remind yourself of what we discussed in the starting of uh, discussion of m is equal to 0 part. We discussed that if the first element fights with the second element, then second element will be surviving for sure and first will be died for sure in the increasing order of attack value. Can we use this here? Yes. First element fights second element fights third fights fourth is surviving. Now we had a construction beforehand. 6 5 fights 5, 6 is surviving. Now 6 fights 4. 4 is dead for sure because 6 has higher attack power than 4. And 4, let's say 4 has health value 1. No matter what health value it is having, the attack power of 6 is more than the attack value of 4. And health value of 4 is always smaller than equal to attack value of 4. So 4 will be dead for sure. And can 4 kill 6? Yes, we have already discussed that this suffix is enough to kill 6. So both 4 and both 6 will be dead for sure in this scenario. But there is also a scenario that is we are having only 3 and 2, 2 and 3. So this 3 can never be killed using its prefix. So in this case, the answer will be minus 1. Alright. Now, what did we construct? We said that first find the suffix index using which we can defeat nth element for sure. If we can find, okay, if we can't find such index, what is our answer? It is minus 1. But if we can find, what is our construction? The prefix up till I fights consecutively. That is 1 fights 2, 2 fights 3, 3 fights 4. Then suffix fight. At the end, we are left over with no elements. All right, all the elements have killed each other. So let's move to the implementation part. This is all for the logic. Let's move to the implementation. So what did we intended? We intended to have health value and attack value for each element. Okay. So the very first observation that we had is if m into 2 is greater than n, we can of course not have uh, those number of pairs in our array. So print -1 and return here itself. Now the first condition where m is equal to 0. Create a array using the element and its index, then sort it. Why? Because we are fighting in the sorted orders every time. Now find the index, the first index which can kill the last element for sure. Start from the n-2th index up until 0th index and move downwards. Add the current attack value. If the using all these current attack values, we can kill the last element. This is the index of our consideration. Break right here, and if j is equal to -1, that is no particular index exists. J, this particular condition has never been fulfilled, so j is -1. Print -1 and return here itself. If such an index exists, what did we say? Apply the operation up until the current prefix up until j. Okay, how? Ith element attacks I minus 1th element, so that the uh, criteria of every element having attacked one of the element is fulfilled. Now, starting from the n minus 1th element, keep attacking in the suffix order. Note that j has already attacked, so j plus 1 should attack. So the order is n minus 1 attacks n minus 2, n minus 2 attacks okay, n minus 1 itself attacks uh, I minus 2 and so on. Okay, now at the end, print the size of answer and print the answer. Now for the second part, where m is not equal to 0. Where m is not equal to 0, create that sorted temp again. What did we intended to do in this part? Okay, we intended the very first m pairs to fight with the next m pairs, and then we have a set of m elements which have already fought and they are surviving. Then next rest elements need to be inculcated. All right. So for that, create the sorted temp. Now the m minus 1 elements fight the next m elements. That is the first m elements fights the next m elements. Now the first surviving element. The first m elements fight with the rest next m elements. They had lesser attack value. They had higher attack value. So these will be surviving. All right. So m plus 1, m plus 2 up until 2 into m minus 1. These are surviving, and 2 into m needs to be inculcated. So inculcated with the very first element, and we are sure that this will be dead because its attack value is smaller than this element's attack value, and it will be replaced with this value. And since this has not attacked before, this will attack the first value. So this is what we are doing. We have assigned cur as m. Now ith element attacks the cur element. Cur is plus increased by 1 at the end, print it in the form of answer. That is it. Uh, that is it for the discussion of today. We will be meeting tomorrow for lead code discussion. All the best for the contest. Thank you.